Hello. Hello.
Yes, sir, you are audible.
Yeah, thank you. Thank you for giving me opportunity to introduce and chair the session. It's my pleasure to introduce Dr. Manasa KJ. She was my senior at the time of MSc in Mangalore University. She completed MSc in the year 2015. She has done PhD from NITK Surathkal under the guidance of Professor B.R. Shankar in the field of imaginary quadratic fields, elliptic curves, and Pell surfaces. She has more than 8 years of teaching experience. She has more than 9 years of teaching experience. Her area of research is algebraic number theory, elliptic curves. She has already delivered many invited talks and published many papers. It's a time to listen Dr. Manasa KJ on the topic the congruent number problem. Thank you, madam. I request Dr. Manasa KJ to present.
Good afternoon to all. Am I audible?
Yes, madam.
Okay. Thank you, Dr. Chandru, for introducing me to the audience. And first of all, I would like to thank the organizer for giving me the opportunity to give a session on today's International Congress on Conference on Discrete Mathematics and Combinatorics 2021. I have chosen the topic as the congruent number problem. Let us see how far I will be able to complete it with the given time. This is one of the problem in the number theory. The number theory is a branch of mathematics that studies various properties of integers and rational numbers. Many of you might have heard the Gauss saying, mathematics is the queen of the sciences and number theory is the queen of mathematics. And the Kronecker also said that the God created the integers, the rest is the work of man. So in this branch of maths, we mainly concentrate on the various properties of integers and rational numbers. Here in this area, we come across many problems or the conjecture which are easy to understand or easy to state. When you are going to prove it, it requires the sophisticated tools of maths. It is not very easy to prove it. For example, you might have heard the Fermat's last theorem. The statement is very simple. Everyone of us heard about Pythagoras theorem in the school itself. That is, if you have got the sides of a right triangle as x, y, z, then the hypotenuse square is equal to sum of the square, which has infinitely many integer solutions, non-zero integer solutions. But when you increase that power to 3 onwards, that is, if you generally write it as x to the power n plus y to the power n is equal to z to the power n, then when n is greater than or equal to 3, it becomes a Fermat's last theorem that it has no non-trivial integer solution. It has taken various centuries together to prove it, and in the year of 1996, the Andrew Weil could prove it using the very sophisticated tool which is known as the elliptic curves. And then later, you might have heard that another conjecture which is a Goldbach conjecture. It is also very easy, even the school students will be able to understand the statement, but when you are trying to prove it, it is very hard. Goldbach's conjecture is nothing but every even whole number greater than 2 is the sum of 2 prime numbers. For example, if you consider the 4, it is the next prime to 2 and it can be written as a sum of 2 prime numbers as 2 plus 2. When you go for 8, it can be written as 3 plus 5. When it is 10, you can write it as 3 plus 7. It goes on. It is easy to understand, but still the proof is not known. To this list, we are going to add one more, the conjecture which is known as the congruent number problem. This is what is my topic of today's session. In this session, I'll be using the two notations, that is Z, which stands for set of integers, and the Q, which stands for set of rational numbers. Here, what is a congruent number? A positive integer n is called congruent number if there exists a right angle triangle whose sides are rational numbers and whose area is a given number. Here you need to concentrate on sides are rational numbers, and when you find the area of the right angle triangle, there is a half into base length and the height. When you take the product, it will give you a number that is n, which is called as a congruent number. For example, if I consider right triangle with the sides as 3 by 2, 20 by 3 and the hypotenuse as 41 by 6, the moment you find the area, that is half into 3 by 2 into 20 by 3, that will give you the area as 5. So 5 is an example for a congruent number. Similarly, if you consider the sides of a triangle as 3, 4, 6, then when you find it is, of course, it is a right angle triangle because 6 square is equal to sum of the squares of 3 and 4. Therefore, it represents a right angle triangle with integer sides, and its area is easy, half into 3 into 4. So 3 into 2, which will be 6. This is also another example for a congruent number. So if I represent the statement in the equation form, we need to solve these two algebraic equations. One is, first of all, sides of a right angle triangle, let us consider it as x, y, z. Then it has to satisfy the square of the hypotenuse must be equal to sum of the squares of the other two sides. And the area, that is half into base into height, x into y, must be equal to n. And we want the rational solution for these simultaneous equations. So how are we going to get it? Before proceeding to the method to get the solution for the above simultaneous equation, let us consider another property of this congruent number. That is, suppose n can be written as u square v, where n is an integer. That is, you are going to removing the square part of the number, then you are left with the v, which is a square-free integer. Then, if n is a congruent number, if and only if v is also a congruent number. Why? Suppose n is a congruent number means we are having a right angle triangle with sides x, y, z, having the area as n. Now, consider the sides of the triangle as x by u, y by u, and z by u, which also represents a right angle triangle, but the area will be now v. So therefore, v is a congruent number. Conversely, suppose v is a congruent number, then there exists a right angle triangle with the sides as say ABC. Now you consider another right angle triangle with the sides as multiply each of the sides by u. So UA, UB and UC. The area of that right angle triangle, that is a half into UA into UB, that is U square into half into AB. You know that half into AB has the area as V, therefore U square V, which is N. So this is a if and only if condition. So now onwards, it is sufficient if we consider the congruent number as the integer which is square free. So we are going to remove that square. So we are having now the congruent number which is an integer, as well as we don't have it is a square free integer number with the right angle triangle having the rational sides, and the area will be square free integer n. The one way of getting this congruent number is using the Pythagorean triple. As I mentioned, in the school you have come across Pythagoras theorem. That is, if you have got a right angle triangle with integer sides, then it will satisfy equation of the form x square plus y square equal to z square. For example, 3, 4, 5 will satisfy this equation in the same order, and 5, 12, 13 also will satisfy. 196 will be sum of the squares of 5 and 12. Similarly, 8, 15, 17. And Euclid has given all the solution, all the integer solution to this equation. If you pick any of the elementary number theory book, you will be getting the proof, how to prove this. How to get all the integer solution to the algebraic equation x square plus y square equal to z square. So in this case, what is that x? X will be m square minus n square, and y will be 2mn, z will be m square plus n square. For integers m and n with m greater than n greater than 0 and GCD of m comma n is 1 or they are co-prime. Converse is also true. That is, if you are able to get such integers m and n which are co-prime and m is larger than n, then you are able to get the primitive Pythagorean triple. Primitive means there is no common divisors between x, y and z. So conversely, you are able to get such a Pythagorean triple from this expression itself. So how are we going to use it to get the congruent numbers? As we know that whenever you are having two integers m and n which satisfy these two properties, then we are able to get sides of a right angle triangle with the integer length as x, y, z. Now only thing which is left out is area of the right angle triangle must be the given number. If that is the case, then n will be our congruent number. So once you have produced this x, y, z using m and n, then we are able to construct the congruent number as follows. Just you consider n as, take the product of the base and the height, the 2mn, that is a length of y and x. X is m square minus n square. So n is equal to half 2mn into m square minus n square. This is what is the required congruent number. So like this, we are able to produce lot many congruent number. Choose any integer m and n which satisfy these two properties. From that, you are able to generate the congruent number. But the question comes, if I give any integer, how will I know that whether the given number is a congruent number or not? Or in this way, are we able to produce all the congruent number? Let us take few examples here to which has been generated using the Pythagorean triple. That is here. Let us consider m is equal to 2 and n is equal to 1. Then how to get x? X will be m square minus n square. That is 4 minus 1 will give you 3. And y will be 2 times m into n. That is 4 itself. And z will be m square plus n square. That is 4 plus 1, 5. And the area of this right angle triangle is 6. And I have also attached another column over here which will give only the square free part of the congruent number n. We know that that also is another congruent number. So like this, we are able to produce lot many. Here also, in this case, when you take m is equal to 4, n is equal to 1, then we are going to get the lengths of the sides of the right angle triangle will be 15, 8, 17. And when you use this formula, you're going to get the area which is equal to 60. Now 60 is obtained by 2 square into 15, that is a 4 into 15. So next here we are able to get 15 also another congruent number. How it is another congruent number? For which triangle it will be another congruent number? Just you need to consider the sides of the triangle, you are allowing it to be rational number. In the Pythagorean triple, you are going to allow the sides of the triangle to be an integer itself. But here we are allowing it to be rational number. So now dividing by 2 here, we will be getting 15 by 2, 18 by 8 by 2 and 17 by 2. So when you take the area of that triangle half into 15 by 2 and here the 8 by 2. So we'll be left with the congruent, we'll be left with the triangle having the area 15 itself. So that is 15 is also a congruent number. Similarly, we can go with some more examples here. The 4 and 3, m is equal to 4 and n is equal to 3. Then we could generate a congruent number which is 84. When you remove the square part of it, we'll be left with now just 21. So what is a square part here? That is again 4. So divide by 2 throughout. 7 by 2, 24 by 2 and 25 by 2 will be the sides of the triangle which will give the congruent number as 21. Same way, if you go with this example where m is 7 and n is 2, we are having the right angle triangle with the integer sides as 42, 28, 53. The congruent number which you are going to generate is 630 and the square free part is 70 and the square part is 9 here. So if you want a triangle with right angle triangle with the rational side and having the area as 70, just divide this 42 by 3, 28 by 3 and 53 is also by 3. Okay, this is what we are going to get. This is the way in which we are able to generate the many more congruent number. But we want to answer the questions which I have posed before itself. That is, how do we know the difficulty is determine whether a given integer n is a congruent number or not? And if our n is not appeared in the list whichever we have produced using the Pythagorean triple, are we able to say that it is not a congruent number? It is not so easy because even though congruent number is small, say 157, to get this 157, the sides of the triangle, only I have written the base and the height, hypotenuse is still bigger, so I have not written over here. It will be of this form, such a big number. So if you have not got it in the list, it says that you have not considered the algorithm. You should have considered the more number of steps to get the number which is required. So it is not a good algorithm. So are we able to get a better algorithm to decide whether the given square free integer is it a congruent number or not? That is what we are going to see here. Let us here in the above list, we have seen one has not come. One has not appeared here. Are we able to say that 1 is not a congruent number or is 1 is a congruent number? That is what is the next question. This was first posed by Fibonacci and he has conjectured it as 1 is not a congruent number. Later, Fermat gave the proof of it using his technique which is known as infinite descent. And this way of proving is also adopted later in the elliptic curves. Many of the proofs are given using the descent method. So here, let me give the proof of telling why 1 is not a congruent number using Fermat's technique, that is infinite descent. It goes in this way. First, you are going to prove is by contradiction. First, let us assume 1 is a congruent number. The moment you tell that 1 is a congruent number, you are able to find a right angle triangle with the rational sides. Let us take that rational sides as P by Q, R by S and U by V. By Pythagorean theorem, we know that hypotenuse square has to be equal to sum of the other two square. And the area of this particular right angle triangle must be equal to 1. Now clearing the denominator by multiplying QSB, we get here PSV square plus QVR square equal to UQS square. Therefore, the area will be half into base into height, or let us rewrite this, half into P by Q into R by S. It will give back to the same terms. Q will get cancelled, S also will get cancelled. We'll be left with same area part. This is a square. So what did we get here? If 1 is a congruent number, then we are able to produce a right angle triangle with integer sides, these are the integers, and area is a perfect square. Area is a perfect square. Let us see, are we able to construct such triangles or not? Let us have, since we are having the integer sides, so a right angle triangle with the integer sides means by Euclid theorem, we know that A can be given as is U square minus V square, and the hypotenuse can be given by U square plus V square, and B will be 2UV and GCD of U comma V equal to 1. All of them are integers. And the area is a square. Area is a square. And how do you get that square? Half into base into height. What is the base here? Base is U square minus V square and height is 2UV. 2 get cancelled and we'll be left with UV into U plus V into U minus V. Since GCD of U comma V is equal to 1 or they are co-prime, we know from the unique factorization, the prime factors are each number uniquely written as a product of prime numbers. Using that unique factorization theorem, we can say that each factor in the right hand side has to be square. So let us consider the first factor, that is U as M square and V as N square and U plus V as L square and U minus V as K square. Now let us produce another right angle triangle with the sides as L plus K, L minus K. From where are we getting L and K? That is from here. Because D square area is a square, so right hand side each factor has to be square. So when you have considered each factor as a square, here you have got L and K. So from that you are going to produce or construct another right angle triangle with the sides as L plus K, L minus K and 2M. Why it is a right angle triangle? Let us see. Sum of the squares of the other two sides, that is L plus K whole square plus L minus K the whole square. When you expand, plus 2LK minus 2LK will get cancelled. And the first two terms you are going to add. So 2 times L square plus K square. And L square plus K square, that is here, L square is here and K square is here. When you add, what you will be getting? That is 2U. So this is same as 4U And here we can replace u by m square, or this will be 2m square. We have got the hypotenuse square. So L plus K, L minus K and 2m forms a right angle triangle with integer sides. And what is the area of this triangle? Half into L plus K into L minus K, which is same as L square minus K square. So when you subtract over here, we are going to get V itself. 2 will get cancelled, V. And what is V? V is n square. And where is this V? V is from this expression. D square is V into something. So V is less than D square. What is V? V is n square. So n square is less than D square. It means we could construct a right angle triangle with the square of a number which is with area as a square of another number which is less than the earlier square, that is the D square. So, if you continue like this, we know that square number is always a positive. Whenever you are going to get a triangle with integer side and having the square as the area, we can construct another triangle with the integer sides and the area will be square of another number which is smaller than the earlier one. This cannot be continued because the positive number less than the given positive number, there are finitely many. So we are going to get a contradiction. This is known as an infinite descent. This is one of the famous technique which is used by Fermat. So we could prove that 1 is not a congruent number. The next, how are we going to get now the other method to construct the congruent number? That is, I have named it as alternative method. So let us go back to the definition of the congruent number once again to get into the another alternative method to know whether the given square-free integer is a congruent number or not. We have got these two simultaneous equations and we are searching for a solution in the field of rationals. Let us multiply the equation 2 by 4, add to the equation 1 as well as subtract from equation 1. So when you multiply by 4, you will be getting 2xy. When you add, it becomes x plus y the whole square. When you subtract, it becomes x minus y the whole square. And the right hand side will be as shown here. The next thing what you are going to do is, let us multiply here. Let us divide these two equations. You are going to divide by 4. So this will be same as x plus y by 2 the whole square equal to z by 2 the whole square plus n. And the second equation becomes like this. X minus y divided by 2 the whole square equal to z by 2 the whole square minus n. When you multiply these two equations together, we will be getting x square minus y square divided by 4 the whole square equal to z square by 4 the whole square minus n square. That is what is the next equation. That is here. Now, thus the rational right triangle with area n produces a rational solution to the equation. We are going to call this, rename the expression whatever is present to the left as u square minus as v its square, and the right hand side as this one we are going to call it as u. What is u? Z by 2, and here this is n square, and I should have written here u as z by 2 the whole square. Missing here z by 2 the whole square, then u square will be z by 2 to the power 4. Now multiplying the equation 6 by u square, what do we get? This will be uv square is equal to u to the power 6. Okay, yeah, here, yes. So this should have been, this is right, u is equal to z by 2, and here it should have been u to the power 4, right? Here it should have been u to the power 4. So when I multiply by u square, then I'll be getting u to the power 6 minus n square u to the power 6. Once again, you are going to rename this expression as the left hand side term. Here we are going to represent as y. So what is this y? Y is u into v. What is u? U we got it as z by 2. U is z by 2 and v is x square minus y square by 4. When you multiply these two together, we are going to left with z into x square minus y square by 8. That is what is y. And what is x? X will be this one, that is u square. What is u square? Z by 2 the whole square. So the expression in 7 can be rewritten as y square equal to x cube minus n square x. So this represents a curve. And what are the points on this? There is an x coordinate on this curve will be z by 2 the whole the whole square, and the y is here z into x square minus y square by 8. This curve belongs to a very famous branch of number theory that is known as the family of elliptic curves, which I'll come tell about that later. So you started with a right angle triangle having the rational sides and the area as the integer n. We could produce a solution to this equation y square equal to x cube minus n square x. With x as, take that hypotenuse z by 2, its square, and y will be z into x square minus y square by 8. So one way it is done. You started with the right angle triangle, we could get a point on the curve as given in 9. Is the converse also true? If you are able to get points which satisfy that two rational points, these are the rational numbers, you can see x is a rational and y is also a rational number. If you are able to get a rational number or the solution for the equation 9, are we able to get a congruent number? That is what is the converse part of this. Answer is yes. I have given in terms of proposition. It goes like this. If x naught comma y naught belongs to Q such that y naught square is equal to x naught cube minus n square x naught. Suppose x naught satisfies the following criteria, that is x naught is a square of a rational number, x naught has even denominator, the numerator of x naught is relatively prime to n, then there exists a right triangle with rational sides and area n which corresponds to this particular x naught. Let us try to give the proof to this. As they have told, x naught is a square of a rational number. Let us consider it as u square, where u belongs to q, and set v as y naught divided by u. Y naught is known and u is also known. And squaring it, we will be getting y naught square divided by u square, which is equal to y naught square, which is same as x naught cube minus n square x naught divided by u square, which is same as x naught. When you divide, we will be getting the equation 11. X naught square minus n square. Or rewriting, we will be getting x naught square is equal to n square plus v square, where n is an integer. X naught is a rational number and v is also a rational number. You can see from this relation, x naught as well as v will have the same denominator, And we know that denominator of x0 is an even number. Let us consider that as a t be the denominator of u is coming from here, and x0 has a even denominator, therefore 2 has to divide t. Also, v square and x0 square have the same denominator by the expression 12. Now multiplying 12 by t square, we are going to get t square n here, t square x0 square is equal to t square n square plus t square b square. So it satisfies the Pythagoras theorem with the hypotenuse as t square x0 square, t square x0, and the other two sides will be like this, t square v and t square n. Okay, so this is a primitive Pythagorean triple of integers. So using the Euclid theorem for the Pythagorean triple, what do we get? The first two sides, that is a t square n, will be 2 times m into n, and t square v will be m square minus n square. You can change the order here as t square v comma t square n, because the middle one I have always taken as 2 times m into n. The first one base is t square v will be m square minus n square, and the hypotenuse will be m square plus n square. Now from this we are going to construct the sides of the right angle triangle as x equal to 2m by t, m and n we have chosen, t we already know, denominator of u, which is a square of, x is equal to u square. So 2m by t and y will be equal to 2n by t and z is equal to 2u. So now let us take x square plus y square. We want to check whether we are going to get this sum of the square is equal to hypotenuse square. Yes, indeed. Here numerator will be 4 times m square plus n square plus n square. We have taken it as t square x0, t square will get cancelled. We'll be getting x0 square, or we'll rewrite it as 2u the whole square. 2u is same as z square. And what is the area of this triangle? Half x into y, that is half 2mt into 2n by t. When you simplify, we'll be getting back to the congruent number n. So what did we do? We have started with a rational number on that special curve, congruent curve. Then we could generate a right angle triangle with the rational sides and having the area as the integer n. So there is a one-to-one correspondence between the rational points on that particular curve and the right angle triangle with the rational sides having the area as n. Still, when you simplify this correspondence, we are going to write it as in this way. The one side I have already shown. This is the same as in the first part. The other part is just you need to do some more simplification of the previous result. We'll be getting this correspondence. What is that correspondence? If you are having the right angle triangle with the sides as PQR with the area as n, and another set with the, importantly here, y is not equal to 0. And the rational points on this curve, then whenever you give the rational sides of that particular triangle, we are able to get the rational points on this curve. And if you have got the rational points on the curve x, y, we are able to get the right angle triangle with the rational sides as given here. That is, a p will be same as x square minus n square by y. You are dividing by y, so y should not be equal to 0. And the q will be 2nx divided by y, and r will be x square plus n square divided by y. As I mentioned, when I have defined the congruent number itself, I have taken this simple example. That is 6 is a congruent number where the right angle triangle has the integer sides as 3, 4, 5. Now let us produce or let us find using this correspondence one of the rational points on the elliptic curve. That is, just you are going to substitute over here r square. R square is 25 divided by 4. That is the x coordinate, and the y coordinate you need to simplify this expression. You will be getting minus 35 by 8. Let me take another example going in the other way direction. You know the rational point on this curve. Let us consider one particular curve as y square equal to x cube minus 7 square into x. And you can easily check that 25, 120 is a point on this curve. Then how are we going to construct a right angle triangle with the rational sides? That is, the P will be, take the x coordinate and square it, minus n in place of n square, we are having 7 square, divide by y is 120. When you simplify, you are going to get it as 24 by 5. Similarly, for Q, that is 2n into x divided by y, you will be getting 35 by 12, and R will be 337 by 60. So when you find the area, you will be getting 7. So 7 is a congruent number because we could show it just by having a solution on the curve, which we have derived y square is equal to x cube minus n square into x. Okay. So the question whether n is a congruent number reduces to the question of finding a rational point x comma y where y not equal to 0 on the curve, that is En y square equal to x cube minus n square x. And this curve is known as an elliptic curve. So we have reached to give a one-to-one correspondence between the congruent number and the elliptic curve. So elliptic curve, it has a very wide application in various parts. It has been used to prove the Fermat's theorem. Now currently it is widely used for cryptography as well as the elliptic curves have provided breakthrough towards solving the congruent number problem. That is, how to know whether the given integer is a congruent number or not. Let me quickly go through. I will not do the technical part of this elliptic curve. Just I am going to give the flavor of it. So it is a equation which is of the form on the left side it is y square, onto the right side it is a cubic equation where these points are taken from the field on which we are interested, and along with that one point we are going to consider that is known as a point at infinity. I will not talk about this. You have to go to the projective plane and all. Morning Vadra sir was telling something about the projective planes. So from that only you are going to get here projective space, projective plane. From there you are going to see why did we introduce this point. And when you consider the right hand side, it should have the distinct roots, or that it should be non-singular curve. Then only you are going to say that it is an elliptic curve, and the discriminant of this elliptic curve can be given like this. It should not be equal to 0. The moment you say that it has a distinct roots, the discriminant will be non-zero. Normally, you are going to, for the cryptography and all, you will be using over a finite field FP. Otherwise, here for the congruent number, we are going to use the elliptic curve over the field of rationals. One of the nice property about this elliptic curve is the points on the elliptic curve forms an abelian group. So what is that law of composition you are going to define? If you have got 2 points on a curve, on the elliptic curve P and Q, you are going to draw a line passing through the 2 points P and Q. Let us say it meets the third point at R, then reflect that point R about the x-axis, where its reflection is known as the addition of the point P and Q, that is here. when P and Q are distinct. If P and Q are one and the same, we will be taking a tangent line, and the 2 points are over here only. Third point will be on the curve, and then take the reflection. This will be P plus P, which is same as 2P. So what are the properties it will satisfy? Normally that the point at infinity always taken in the vertical direction, and it is some point above the xy plane you can consider, and it is in the direction of the y-axis. So that composition law will satisfy these following properties. There is L is the intersects E at the point PQR, then the sum P plus Q plus R must be the point at infinity. That is, what is that? Let us go back here. It will be on the vertical line P plus Q, and this we are going to add R. When you are going to add R, this vertical line has to meet the curve at another point. The another point is which is outside this plane. That is a point at infinity. That is what is the O, point at infinity. That is the way in which you are going to consider the sum on the points, or sum of the points on the elliptic curve. And another property, this O always acts as the identity. P plus the point at infinity will give you P itself, then the abelian commutative property. And similarly, you are having the inverse, which will be denoted as minus P, and the most crucial property, that is associativity, which is hard to prove here. In the law of composition, associative law for proof of this for the points on the elliptic curve is not so easy to prove. So you know that now the points on the elliptic curve forms an abelian group. And this, if you are going to concentrate only on the rational fields, that is what we required for the congruent number problem. So E of Q, then this is the way in which we will be denoting the points on the curve, which rational points on the curve along with the point at infinity forms an abelian group, and this group is known as a model Weil group. And when you are going to recursively add a point m number of times, where m is an integer, how you are going to define the order? You know that in a group also order of a point is defined in the same way here also. P has a order m. If when you add P m number of times, you should get the identity, and not for any integer less than m, then you are going to say that P has the order m. And the collection of all such finite order elements also forms a group, or it is a subgroup of the model Weil group, and this group is known as a torsion group, or the torsion. This is the way in which we are going to denote collection of all the points having the finite order. And one of the nice property about the model Weil group in the case of elliptic curve is, if you know, because of this addition property, if you know one rational point of infinite order, we'll be able to generate many more. And not only that, the group is finitely generated. That is, if you have give only finite number of rational points, you will be able to generate all the rational points on the curve. And that how many points are required to generate all the points on the particular elliptic curve is known as the algebraic rank. And the finding the rank of the given elliptic curve is a hard problem. Till now we have it's known that elliptic curve with the largest rank of 28 is known. Beyond that is not known. It's still an open problem. And also, if you are going to concentrate only on the points having the finite order, then it has certain properties. First, Nagel proved that whenever you are the finite points of finite order on this group will have the following property. The both x and y coordinates will be an integer, and if y coordinate is equal to 0, then P has order 2, or else the y coordinate must divide the discriminant of the curve. Using this, we are able to find the many of the finite points on the curve. And if you are going to concentrate on only torsion group of the elliptic curve over the rationals, then Mazur has given one of the beautiful theorem as it has only such orders. That is a finite group of the elliptic curve over the rational. Either it is a cyclic group of the form z by nz, where n varies from 1 to 10. There is no elliptic curve will have the finite group which is isomorphic to cyclic group of here n is replaced with 11. There is no such elliptic curve at all. And another thing is it can be isomorphic to group of this kind. This is also many people are doing the research on finding the structure of the torsion group for various type of elliptic curves by varying the fields. Instead of Q, you can take number fields, quadratic field, pure cubic field, or the biquadratic fields. So then you can find what will be the structure of such group. Still many are doing the research in this direction also. Then next, let us connect the congruent number problem with this field, that is the elliptic curve. For that, we need one of the open problem which is known as a Birch-Swinnerton-Dyer conjecture. It has has been listed as 7 millennium problems, and still it is an conjecture which is not solved, and some of them have given the proof for the congruent number problem, but all those proofs are related to BST conjecture. If this conjecture is proved, then only whatever the proof they have given is valid. So it all depends on the BST. So just I am going to tell here what exactly it relates. That is something called L function, which goes to the analytic property of the elliptic curve. The whatever I mentioned till now, it is only the algebraic properties of elliptic curve. So there is something called L function which looks like this. If you are able to predict that, the BSD conjecture predicts that L e comma 1, the 0, L of 0 of this L function is 1 if and only if E of Q is infinite. The rank of the elliptic curve will be at least 1. R is greater than or equal to 1. So this is the way in which it goes. So now if I go back to the congruent number problem itself, what did we do? A rational point x comma y on the congruent number, a rational point x comma y on the congruent number elliptic curve y square equal x cube minus n square x has infinite order if and only if that y should not be equal to 0. When the moment y is not equal to 0, it means order of the group is infinite. So thus n is a congruent number if and only if En of Q, that is a group, must be infinite. This is the first thing. And the next, what are the progress in the field of congruent number problem? That is, Nagel in the year of 1929 showed that if you consider instead of n integer, you are going to consider particular prime, then is finite for any prime. This elliptic curve equation where n is replaced with the p now, then the group over the rationals for that curve will be finite if the prime is of the form 3p is congruent to 3 modulo 8. Therefore, such numbers, such integers are not a congruent number because we are getting the group is finite. We wanted the group has to be infinite. This is what Nagel has shown. Then Higner, 1952, he has showed that if you consider n as a 2p, where p is congruent to 3 modulo 8, then the group will have infinite order. Then Monsky, he has still updated this in the 1990s for instead of taking 2p, if you take the primes which are of the form congruent to 5 modulo 8 or congruent to 7 modulo 8, then you are going to get the group will be infinite. So these are all congruent numbers. And the later in 2012, the TN has proved that for not only for the prime, for the composite number, but all these proofs are on the basis of BSD conjecture. These are the few references. I started with reading the elliptic curves from this book, which is simple and you can easily understand that the rational points on the elliptic curves by the Silverman. And the Koblis, the most of the content whichever I have given here is taken from the, one is from this paper by Conrad, the congruent number problem, and from the book by Koblitz, Introduction to Elliptic Curves and Modular Forms. With this, I'll end my session. Thank you all.
Thank you, madam. It was a very nice presentation. The madam started with a very basic thing, Pythagoras theorem. She has connected congruent number. Hello.
Yeah, now we are audible, sir. Yeah.
Mute agittu. It was a very nice presentation. She has started with a very basic thing, Pythagoras theorem and simple problems in number theory and their solutions. She connected the congruent numbers and elliptic curves, established the equivalence of that, and also went to very deep into like model Weyl group and model Weyl theorem. Very nice presentation, madam. Any participants questions? Any questions from the participant side? Please raise your hand. If not, I thank the presenter. You can post the questions in the available message box.
Very nice presentation, Manasa. Very comprehensive, nice presentation.
Thank you, sir.
I thank the organizers for giving me an opportunity to chair the session. Thank you. Over to you.
I once again, okay. Can I speak?
Yeah, yes, ma'am.
Yeah, I once again thank to the organizer as well as Dr. Chandra Hegde for chairing the session, and a special thanks to Dr. Prasanna Pujari, who has encouraged me to give the session here, and to the principal of the Poornaprajna College for providing the opportunity to present the session. Thank you once again.
I would like to thank Dr. Manasa KJ for accepting our invitation and for delivering such an impressive and informative session. Thank you, ma'am. I would like to thank Dr. Chandra Hegde sir for chairing the session. Thank you very much, sir. Dear participants, feedback link is available in conference site. Within few more minutes, we'll begin the session on order of finite generation of SO3 and optimization of rotation sequences by Dr. Daniel. Thank you.
Virtual view of our
Dear participants, this is an virtual view of our Karnataka and especially coastal Karnataka, famously known as Tulunadu. Thank you.
ಪರಶುರಾಮನ ಕೃಪೆಯಲಿ ಕಡಲ ಜನರ ನಗುವಲಿ ಹುಟ್ಟಿದ ಒಂದು ಸಂಸ್ಕೃತಿ ನಮ್ಮ ತುಳುನಾಡು, ನಮ್ಮ ತುಳುನಾಡು, ಎಂತೆಲ್ಲ ತುಳುನಾಡು, ಮೊದಲ ತುಳುನಾಡು. ದುರ್ಗದೇವಿಯ ನೆಲೆಯಿದೆ, ಉಡುಪಿ ಕೃಷ್ಣನ ನಗುವಿದೆ, ವಿವಿಧ ಕಲೆಗಳ ಕಳೆಯಿದೆ, ಶುದ್ಧ ಸಂಸ್ಕೃತಿ ಒಲವಿದೆ. ಶ್ರೀ ಮಂಜುನಾಥನ ಮಡಿಲಲಿ ದೈವ ಭಕ್ತಿಯ ಸೊಬಗಲಿ ಕಡಲ ಮಕ್ಕಳ ಕಥೆ ಇದೆ. ಯಕ್ಷಗಾನ ಕಲೆಯಿದೆ, ಕೋಟಿ ಚೆನ್ನಯ ಕಥೆ ಇದೆ, ನಾಗರಾಧನೆ ಇಲ್ಲಿದೆ, ಹುಲಿಯ ನರ್ತನ ನಮ್ಮದೇ, ಕಡಲ ಅಲೆ ಜೋಗುಳದಲ್ಲಿ ಕರಾವಳಿಯ ಉಸಿರಲಿ ಕೋಟಿ ನಮನ ಈ ಮಣ್ಣಿಗೆ.
Shall we start, sir?
Hello. Yes. Can you hear me?
Yes. Shall we start?
Sure. Yes.
Yes. Thank you.
I'm ready. Okay. Shall I turn on the camera? Let's try
Yeah,
this.
sir.
Okay, hello. Just to say hi now. Now I'll switch it off
Hello,
because
sir. Hello.
we need to see the slides. This camera is a bit distracting, but I just wanted to say hi. So I'm gonna first thank the organizers for having me. It's a pleasure to be back to India, even though it's just virtual conference, but it's really a pleasure.
Greetings to all. I welcome back you all. As a resource person, we have with us Dr. Daniel Brizzo, Associate Professor, Department of Mathematics, University of Architecture, Civil Engineering and Geodesy. Our resource person will be talking about the topic, the order of finite generation of SO3 and optimization of rotation sequences. Also, we have with us Dr. Manasa KJ, Assistant Professor, Department of Mathematics, Vidyavardhaka College of Engineering, Mysore. Madam has published several research articles in reputed journals, mainly related to algebraic number theory. May I request Dr. Manasa KJ to chair the session. Over to you, madam.
Thank you, Chaitra. Good afternoon to all. It is my pleasure to introduce the speaker of this session, Dr. Daniel Brizzo, currently who is working at University of Architecture, Civil Engineering and Geodesy. Previously, he worked at European Political University, British School of Sofia, Bulgaria Academy of Sciences. He did his Bachelor's of Science in Physics from Faculty of Physics, Sofia University in the year of 2004. Later, Master of Science in Mathematics from Faculty of Mathematics and Informatics, Sofia University. And he did his PhD in Mathematics from Institute of Mechanics, Bulgaria Academy of Sciences in the year of 2015. His research interests are geometry and mathematical physics, geometric algebras, hypercomplex numbers, and Lie groups in physics, also modeling and simulations of complex systems, statistical and numerical methods, cellular automata, machine learning, and artificial intelligence. He has published several national and international papers, and he was also reviewer for mathematical reviews, Journal of Geometry and Symmetry in Physics, and Springer's Advances of Applied Clifford Algebras. And he was jury member for appointment of academic staff as assistant and associate professors, and also training and organization of regional and international students' mathematical Olympiads. Thank you for accepting the invitation. Over to you, sir.
Thank you very much again. I'd like to thank the organizers again. It's a great pleasure to be here, even though this is not my main field of research, discrete mathematics. I hope what I'm about to say gonna be interesting for some of you. This is a topic which is partly in the field of discrete mathematics and partly in the field of group theory. Actually, maybe a more on the topic presentation I did last time in India. Unfortunately, I can do the same thing again. It's gonna be old news. It was about discrete and rational geometries. Okay, now I'm gonna go to the presentation. Now, what we call order is actually many things in mathematics are called order. So this is one word for many different things. I'm gonna use one definition on the next slide. It will become apparent. But first of all, what is the motivation? Why are we bothering with this, with such things? It's firstly, it's just theoretical curiosity, so we can learn a little bit more about presentation and the composition of rotation and unitary groups in low dimensions. So I'm interested in particular in SO3 and SU2. So these are, I'm going to talk about the rotation group, but the other one is locally identical. So So it's just going to be a matter of plus and minus factor. So all the results will be applicable to quantum mechanics, for example, spin systems and many other fields which use this SU2 group. So for instance, quantum computation is one of them. Now, apart from this pure theoretical study, of course, the applications apart from quantum mechanics, I already mentioned, also computer vision, VR technologies, things like that. We are interested in rotation in relation to aircraft and spacecraft maneuvers, for instance, or navigations. And of course, the main reason we do mathematics is that it's entertaining, it's a lot of fun, right? So what is exactly an order? Finite generation, I modified a little bit this. So I'm using a definition that's suited for the purpose of this talk, right? And so let's say we have a Lie group and a collection of subgroups, of a billion subgroups. And if we can represent every element of the groups or arbitrary element of the group as a decomposition with elements of all the subgroups or some of the subgroups, we're looking for the shortest length of this representation. So if we the minimal number of factors in the decomposition, so to say, right? We call this order of finite generation. So this is a little bit more general than other authors use, but it's well suited. So it's a very flexible definition. Now, in particular, I'll be interested in groups of motion. So I'll say, what is an abelian subgroup? Well, let's take a plane. Let's take a plane in Euclidean 3 space, and the subgroup of rotation within this plane is an abelian subgroup of SO3, right? So if you have two such planes, or in dimension 3, you can think as of axis of rotations, right? In higher dimensions, you can do this, but so let's say you have two axes of rotations, and the question is, what is the minimal number of factors you can use to represent every rotation using only these two axes, right? So this is the general idea. So if these two axes are orthogonal, it is a well-known result. This is the classical Euler angles, right? A little bit more general is all result of Lowenthal, proven in 1971. So let's say gamma is the angle between the two axes, and then you have such an estimate for the order. So this notation here means we round this number from above, right? So this is not the integer part, but this is the minimal integer number that is greater or equal to this fraction here, pi over gamma. And for instance, of course, if gamma is pi over 2, we have 3 factors. This is the classical Euler setting. If we have, for instance, gamma equal 60 degrees, we have 4 factors. With 45 degrees, we have 5 factors, and so on. So this very, very simple formula for the finite order of generation has been proven in an extremely surprisingly complex way. So the author used advanced complex analysis, special functions, advanced geometry. And I was wondering if we can do this simply enough to present to students. Maybe include this in an undergraduate course or something like that. And it turns out it's possible to use a little, very little bit of spherical trigonometry. So mostly it is the triangular inequality and a little bit of trigonometry. Now, some generalizations are due to Hamada, a Japanese mathematician, who used to consider this question for not for the whole group, but for some subset, for instance, subset, or even for one representative of the group. So let's have a rotation and see what the minimal length or the order is for this particular rotation. This is a very interesting study, and we're going to do something like this. Another thing is that we have the generalized Euler decomposition problem resolved in closed form, both for the rotation group and the three-dimensional Lorentz group, so the non-commutative version. These both results appear in 2014. Okay, so a little bit about notation. So we think of rotational axis. It's somewhat easier, or more generally rotational planes, but it's somewhat easier to work with the unit vectors along the axis, and we orient those vectors. So the orientation is arbitrary, of course, but we orient them so that we can use only half the sphere, right? So it's just it's actually projective plane, but it's easier. It's locally identical to the sphere. It's easier to work on the sphere, and we think of spherical triangles, spherical cosine theorem, things like that. And so we use on half of the sphere. So gamma will be the relative angles between two rotational axes. So in the spherical polygons, this would be the length of the side of the polygon, because we're on the unit sphere. Beta will be the angles each of those axes makes with the compound rotations axis, right? The one we want to decompose, say. And this tilde gamma would be the shift. So let's say we have an axis, the compound rotation shifted somewhere else on the sphere, and we see how far it goes. So this would be gamma II, for instance. The two indices are the same. And if they're different, it's one of the axes is shifted, the other stays in its initial position. And so I'll stop saying axis, I'll say just points on the sphere, and we just measure the distance between those 2 points. So this is basically what's happening. Phi I would be the angles in the decomposition, and phi with no index would be the compound rotation angle. So these are just notation. Okay, so we go on with some very simple results. For instance, this gamma tilde gamma ij is restricted. It's very easy to prove this. It's restricted between so this gamma ij again is the initial angle between the two axes. Gamma with tilde is when one of those is shifted by the compound rotation, and we have such an estimate. It's a combination of triangle inequality and just introducing spherical coordinates in a convenient way. So it's very simple to prove. Also, this, yeah, we'll talk about this later anyway, so I'll skip this part. But one place to start is the composition into two factors, right? So it's well, two factors is a bit tricky because we have three parameters. It's a three-dimensional group, so so to say, it's a zero measure set within the group. So if it's decomposable into two factors or not, it's not clear at all. But there's a simple condition. By the way, it's related to Rabi resonance. They use this very much in quantum computers. So this gamma tilde should be equal to the initial gamma. So the rotation acts on one of the axes in such a way that the angle between the two remains the same. So it rotates one of the axes. So it's actually a circle, right? So I should have put this picture here. So it's a map on the circle. So one of the axes is in the middle of the circle, the other is somewhere around it. And so the compound rotation takes one point of the circle and puts it in another place. So it doesn't go outside. So this is a little bit. So it's a bit technical. I'm not going to say how exactly we obtained it because there's a new tool we need to introduce. But just because of this determinant at the end, so this would be the case of three factors. So the necessary and sufficient condition would be a determinant like this. It's a symmetric matrix, so actually it's equivalent to the existence of a rotating frame. So we think of one frame which is fixed, the three axes in the decomposition, and there's a dual frame which moves together with the, let's say, some rigid body we're studying, things like that. So this would be the grand determinant of the rotating frame. So it's always, of course, positive definite or non-negative at least. So this is actually this inequality says that this exists, and we can write it in terms of the angles in such a way. This is a Cayley's nodal cubic, also known as spectrahedron and many other. So this thing appears from time to time. This is not anything new. Now we'll see how it works with four factors. But first of all, it's very easy if we, like in the classical Euler decomposition, if we put the first and the third axis, if we make it the same or parallel, right? Because the lower bound just disappears, and we have this tilde gamma 3,1 equals twice the angle between the axes, right? So we'll see something like that appearing over and over again, increasing the number of factors. But let's see first how it works in the case of 4. So once we have the explicit solutions to the case of 3, we can obtain explicit solutions for the case of 4 if one of the axes is repeated. Doesn't matter where. So we actually have 4 factors with 3 axes. And we have a very similar necessary and sufficient condition for each particular case. Actually, what it says is that when you start, so these are again points on the sphere. these axes of rotation. They are mapped on the unit sphere's point. So you start from the first one, and you go. You follow a geodesic to the second one, so to the third one, and so on. So you follow a closed geodesic path, right? And this is so it's not always closed. It's closed just in the first case. Sorry. So you follow the geodesic path. So it tells you that this gamma tilde should not exceed the length of the geodesic path. Okay. This is the same in the case of 3. In the case of 4, I will prove by induction that it works. It works for longer decompositions, and we use this for to retrieve our result for the order of finite generation. So first of all, let's make things simple. So for these last few slides, I use the results that are derived with some calculations. And if I have to explain this to first grade student, I have to make him or her first read, maybe 100 pages. So the point is whether we can do it very simply using triangle inequality, simple tricks that are available to students, some of them even from high school mathematics. So this is the flower. This looks like the flower of life. Actually, I took the picture from the internet, but otherwise I should have drawn the same picture. So in the middle is one of the axes. Here, this inner circle, somewhere around it, is another one. And because we use conjugation, the question is how far this second axis can move the first one, right? How far can it go? Well, this is how far it can go on the outer circle. So because we use conjugation to represent this 3-factor decomposition into 2-factor decomposition, and one of the axes is shifted, right? So it should be shifted in such a way that the condition for 2 factors holds, and the inequality. So we need to have incidence, right? So it's an incidence relation actually, and the inequality tells you how far you can go, the longest distance you can move, you can shift this axis. So this is the simple way when you have the 2 decomposition condition to translate the 3 decomposition condition into this without obtaining the actual solutions. We don't need them so far. We need some geometry, or very, very simple basic geometry to represent this in terms of distances, for instance. So we can use the Rodrigues formula for rotations, or spherical geometry to obtain this inequality in terms of Haber-Sein distance, for instance. We can also use something else when, in some cases, we don't know anything about the compound rotation angle, for instance, or for its axis. So we can use only one of these 2 features, right? And if we're not certain about one of them, we still have inequality that guarantees that, for instance, whatever the axis is, if phi is restricted in this way, if the angle is restricted in this way, we have a decomposition. Or alternatively, whatever the angle is, if the angle between the axis and the first rotation axis is like this, we have a decomposition. So for the next step is to make an estimate from below. This is very simple, actually. We said that this gamma, the shifted angle, should not exceed the length of the geodesic path. This is, in general, this is only a necessary condition for the decomposition. It's not sufficient, but when we restrict to 2 axes, it would become also sufficient. So this estimate for the order of generation, this estimate here, would become equality in the case of 2 axes. Still, I think it's useful to have, in the more general case, to have such an estimate, to know what to expect at least. So this gamma bar would be the mean distance or the mean length of segments in the broken geodesic on the sphere that connects the points representing the axis of rotation. So this is already close to Lowenthal's result, but even closer when we take close paths. So the first and the last one are equal. The first and the last axis coincide, like in the Euler decomposition. There, the distance can be written in a very simple way. And of course, if we know only one of them, so if we have no control on the compound rotation angle or axis, we can come up with these 2 estimates for the corresponding order. So beta would be the minimum. So I can choose which axis to start with. You know, we can commute the order of rotation. So I mean, it's a matter of choice. Not that we can commute them, but it's a matter of choice. So I choose the one which is minimal. So that I can guarantee that the order is, or the length of the decomposition is as short as possible. And of course, this mean distance gamma bar would become gamma in the case of only 2 axes. Now, and these will become equalities, right? So the next slide. I said it's a matter of choice which point you begin with. Imagine that these are all on the sphere, right? And these vertices represent rotation axis. And these distances, they would be, of course, segments of circular segments. They represent angles gamma between the axes. So what I need for the estimate is the geodesic path, right? And the longer it is, the more freedom we have, right? So I can, instead of this orbit, which is the circumference of the polygon, I can take these diagonals. It's also a closed orbit, and this would give me a better chance to represent so a broader subset of rotations that can be represented by this decomposition into 5 factors. So we have a lot of freedom. What about if I take only 2 points? We don't have to always take all the points, right? So we can take only 2 points. Say, take the $2 as far apart as possible, so the longest distance, and make a bouncing ball orbit, right? So this would be this would give us more freedom to represent rotations. Or if we consider the whole group, this will give us shorter sequences. And in this case, yes, the lemma says that for two axes, this becomes necessary and sufficient condition. I put the wrong lemma here, but what I meant to say, I said. And yes, and with this, all these become equalities. The last estimates for the order, and of course, if we don't have either control on either of the two things, the angle or the axis of compound rotation. So we need, if we want to be as general as possible, then we should put pi here. Pi would be the maximum number, the maximum value of both phi and 2 beta, because beta is choose orientation so that angles between axes are minimal. So beta is between 0 and pi over 2 anyway. So from this Lowenthal result immediately, and I will mention some other things that this relates to. So one of them is a bunch of classical theorems in geometry and mechanics, Donkin, Roderick Hamilton, which relate spherical polygons with closed rotation sequences. There is a nice, so I'll just give you a nice reference to this, an article from 2015. And I played a little bit. So these things are not in the article. It just explains, gives classification, it gives nice results, but these things are not in the article. I just played a little bit with my explicit solutions and saw that it fits very well in this relation with the classical results. And so it's generalization, so to say, of these classical results. Also, I mentioned we can transform this from rotations into quaternions, because quaternions, of course, unit quaternions, they are just rotations up to a factor, let's say. So this is the spin group of the rotation group. But also the multiplicative group of quaternions is unit quaternions and non-zero factors. So factors are commutative. So whatever we say for SU2, we can say in this respect about the composition and order of generation. So the same thing we can say about the Lipschitz group or the multiplicative group of quaternions. So this relates also to Clifford algebras, not just for, it's not only about rotations and qubits. This we go from one description into another. It's pretty much standard. So there's a standard representation of quaternions in axis angle variables, and the dot product is also well known. Okay, one more thing which I haven't done precisely, but there's no problem to do this, is go from the homogeneous group, motion group, to the inhomogeneous. So think about Galilean transformations, rotations and translations. And the algebraic way to do this is by introducing dual quaternions. So introduce one epsilon, so hypercomplex number, which is nilpotent, so it squares to 0, and it allows you allows you to represent in a more compact form this semi-direct product. And there's also a transfer principle, the so-called transfer principle, which allows you very easily to transfer results from the compact case of SO3 to non-compact one of the dual group or the semi-direct product. So we have obtained the explicit solution there too for the low order cases. It's almost straightforward, but some details need to be considered. And of course, when you cover the real SO3, you can think about the complex SO3, which is actually the Lorentz group of relativity, special relativity, or the proper Lorentz group to be more precise. These results cannot be directly related to the complex Lorentz group because we have inequalities here which make no sense in the complex case. This is not a complex numbers are not ordered. You can of course generalize the notion of angle. You can generalize a lot of things, but the whole thing, you have a restriction about the composition in the real case is that there's a square root of discriminant in the solution, given for 3 factors. So you have a quadratic equation for parameters, and you don't want these solutions to be complex, because when they are complex, you end up with Lorentz. So you end up with the composition of rotation into Lorentz transformation. So for Lorentz transformation, you don't have this restriction, and you're much more free to decompose, so to say. But for rotation, if it doesn't work for complex ones, perhaps it works for the dual case. So this is the non-compact subgroup, which is really conjugated, so to say, to the rotation group. This is a 3-dimensional Lorentz group, and it's a bit more difficult. I wouldn't do this in the same article, because there are very many specific things one needs to consider. So firstly, because of the different types of vectors with respect to the light cone, you cannot simply talk about angle between two axes. This angle means different things depending on what the axis types are, whether they're time-like, space-like, and things like that. But it would be also very interesting to do this, because it's related to, of course, to relativity, to some other fields of physics, also related to what is this called, symplectic transformations, and interestingly to scattering, quantum mechanical scattering. So you can think of scattering process of particles with respect to some very complex scattering potential. So it's like a black box process. You don't know what's going inside. You just measure the result by these reflection and translation and transition coefficients. And the thing is, sorry, okay. The thing is that you can. The thing is that these directions they represent different states of these potentials. So, for instance, one potential would give zero reflection. So, orientation of the axis so to say. The physical interpretation is zero reflection, or another one could be keep the phase, so not changing the phase of the beam of particles, say. This would be another orientation. So it's an interesting from a physical point of view to talk about these decompositions. This is for the future, and I will stop here because it's already been 40 minutes. I thought I might, not take 45 minutes. It's too much. Everybody's probably a bit tired by now, but I'll be happy to answer questions. And once again, thank you for your patience and for your kind invitation.
Thank you, Dr. Daniel Brizo. Participants, do you have any questions? It's time for asking the questions, or you can put it in the chat box also. No questions? Over to Chaitra.
I'm very thankful to Dr. Daniel Brizo for accepting our invitation and for sharing your knowledge with us. Thank you, sir.
Thank you very much.
I would like to thank Dr. Manasa KJ for being there with us and for chairing the session. Thank you very much, ma'am.
Thank you.
Dear participants, feedback link is available in conference site. Please go through it. We are now at the terminating stage of this program. So, our chairman, ICDMC 2021, Dr. Raghavendra A, will give concludatory remarks within few minutes. So please stay tuned in.
ಸಂಚಾರಿ ಅಲೆಗಳ ಕಥೆಯ ಕೇಳುವ ಗಡಗಡ ಮರೆಗಡ ಮರಿ ಹಾಡು ಕೊಡು ಕಡಲಿನ ನವ ಬದುಕಡಿ ನಾಡು ಕಿವಿಯೋಲೆ ಹಿಂಗಾರ ತೆಂಗು ಬಾಸಿಂಗ ಬಂದೆಂದು ಚಂದ್ರಗಿರಿ ಹೊದೆದು ಸೆರಗಾಗಿ ತವರಿಗೆ ದೀಪಾವಳಿ ಸುಭಾಷಿಣಿ ಸುಹಾಸಿನಿ ಕರಾವಳಿ ಸುರಾಂಗಿಣಿ ನಾಡ ಹೊಳೆವ ಮೂಗುತಿನಿ ನನ್ನೊಳಗಿರುವ ಬಣ್ಣಗಳು ನೀ ಹೇಳಿರುವ ಕತೆಗಳ ಬಯಲಾಟವು
Good evening, everyone. To have a big success in our endeavor here, it was a long pending dream to organize and host an international conference in mathematics. So here, more than being principal of a first grade college, I'll be very happy to be here, to be present as a teacher of mathematics. Being teacher in mathematics for the last 30 years, it's my privilege to give the concluding remark as the principal of the college and chairman of this international conference. Organizers, they will do their duty formally, but from my heart, I would like to thank all the resource persons, starting from Dr. Poornaprajna, to name all. It will be time consuming. Resource persons who have been resourceful as invited speakers, then young researchers, then the scholars who have chaired the sessions. So it's my duty to thank one and all, and I would like to congratulate the organizing team led by organizing secretary Dr. Prasanna Pujari for this successful completion of this international conference. As I said in the beginning, this was a full-fledged international conference having research scholars from different parts of the world participating as delegates, then invited paper presenters, invited speakers, and more than that, as well-wishers of the Department of Mathematics, Poornaprajna College. Poornaprajna College, as some of you may be aware, is situated in a small town, Udupi. City Udupi was just shown in the small video. It's almost a rural area, semi-urban I can call, besides Arabian Sea on the west coast of India. Though it is very small in size, its contribution to banking and education is immense. So many educational institutes have come out here, banking industries have emerged from this area. People of Udupi or this coastal area have been enterprising areas have been good entrepreneurs. Sorry, it was blocked again. Sorry, I was not audible. Am I audible now?
Yes, sir.
Should I start from the beginning or was it disturbed in the between?
Just before 1 minute, sir.
Okay. So I was telling about the contribution to area of research. Okay. There are many scientists, to name a few, Dr. U.R. Rao, famous satellite scientist from this area. That the contribution to research area is not enough. So we as college teachers have to bring out the talents in youth. Okay. So for that, this type of activities which will promote research, which will give opportunity to young enthusiastic researchers was a need of the hour. Therefore, this was being planned for last 2 years. Now, with the hard work and a meticulous planning of the Department of Mathematics and the stewardship of Dr. Prasanna Pujari, very successful international conference has been. I would like to congratulate all the paper presenters, and again from my personal behalf and from the college and from the management and from the organizing team, I would like to thank each and every resource person and the delegate of this conference. Thank you.
Thank you, sir. Acknowledging the good that you already have in your life is the foundation for all evidence. And gratitude turns what we have into enough and more. I would take this opportunity to thank all the delegates, all the invitees for accepting our invitation and for being there with us. I thank all the participants worldwide for your response and participation. I'm very thankful to Poornaprajna Managing Committee and our beloved Principal Dr. Raghavendra A for encouraging and giving us an opportunity to organize ICDMC 2021. I express my thankfulness to all faculty members of the department for the support. Finally, we, Department of Mathematics, Poornaprajna Postgraduate Center, would like to conclude the conference. Thank you all for making this conference a very successful. Thank you one and all. Here is an announcement. Dear participants, feedback link is available. Dear participants, we are expecting feedback from you. Please unmute yourself and speak up. Thank you.
Thank you.
Dear participants, we are expecting feedback from you. Please do speak up. If not possible, please do give your views in the feedback form. Thank you. Thank you, one and all.
Thank you.